Alkanes Video 4 Chemical Properties. The molecular structure of alkanes involves only carbon-carbon and carbon-hydrogen single bonds. As all these bonds are sigma bonds and are partially non-polar in nature, alkanes constituents a rather unreactive class of compounds. They are quite inert toward the common reagents such as acids, alkalis, and oxidizing or reducing agents under ordinary conditions. However, under strong conditions, alkanes do undergo a few reactions, mostly involving substitutions. The reactions generally take place by free radical chain mechanism. The important reaction of alkanes are described as: first, halogenation. This reaction involves the replacement of one or more hydrogen atoms of an alkane by a corresponding number of halogen atoms. I again repeat, halogenation is a reaction involves the replacement of one or more hydrogen atoms of an alkane by a corresponding number of halogen atoms. Chlorination and bromination are carried out by treating the alkane with chlorine or bromine in the presence of light or at high temperature. For example, when chlorine reacts with methane under these conditions, all the four hydrogen atoms of methane can be successively replaced by chlorine atoms as shown below. CH4 plus Cl2 converted to CH3Cl plus HCl. It is obvious there that the order of reactivity of halogens towards alkanes is fluorine greater than chlorine, greater than bromine, then greater than iodine. Halogenation of higher alkanes. Formation of isomeric halogen derivatives. The halogenation of higher alkanes yields a mixture of all possible isomeric halogen derivatives. For example, chlorination of propane gives a mixture of 1-chloropropane and 2-chloropropane. Propane CH3 bond CH2 bond CH3 converted to CH3 single bond CH2 single bond CH2Cl or CH3 single bond CHCl single bond CH3, that is 1-chloropropane and 2-chloropropane. Further chlorination gives a mixture of 4 distribution products which are shown below. That is 1,1-dichloropropane, 1,2-dichloropropane, 1,3-dichloropropane and 2,2-dichloropropane. The mechanism of halogenation is discussed a little later. Note, it may be seen that halogenation of alkanes is an oxidative process because it involves replacement of electropositive hydrogen atoms by electronegative halogen atom and is accompanied by an increase in the oxidation state of carbon. Second is nitration. This reaction involves the substitution of a hydrogen atom of an alkane by a nitro group. It is carried out by heating the hydrocarbon in the vapor state with nitric acid at about 700 Kelvin. RH plus HNO3 at 700 Kelvin converted to RNO2, that is nitroalkane plus H2O. During nitration, rupture of carbon-carbon single bond in some of the molecules also take place. As a result, the reaction furnishes a mixture of different products. For example, the nitration of propane results in the formation of a mixture of 4 nitro compounds. CH3 single bond CH2 single bond CH3 plus HNO3 at 673 Kelvin converted to 1 nitropropane and 2 nitropropane and nitroethane and nitromethane. Third is sulfonation. It is a reaction involving the replacement of a hydrogen atom of an alkane by a sulfonic acid group. Only higher alkanes undergo sulfonation by reacting with fuming sulfuric acid. For example, hexane C6H14 plus H2SO4 in the presence of SO3 converted to hexane sulfonic acid plus water. Nitration and sulfonation are believed to take place by free radical mechanism. Fourth is oxidation, in which first part is combustion. When burnt in excess of air or oxygen, alkanes undergo complete oxidation to produce carbon dioxide, water, and large quantities of heat. Example is CH4 plus O2 converted to CO2 plus H2O, and heat releases is minus 890 kilojoule. In spite of being highly exothermic reaction, combustion requires a high temperature, that is a flame, to start it. This is due to the energy of activation required to initiate the reaction. Due to the large quantities of heat produced during combustion of alkanes, this reaction has tremendous practical importance. Vast quantities of hydrocarbons obtained from petroleum are used as fuels for the production of heat and power by combustion. The cooking gas, commonly known as LPG, is a mixture of propane and butanes compressed as liquids. Incomplete combustion of alkanes due to insufficient supply of air or oxygen results in the formation of soot or carbon black. This is used in the manufacture of Indian ink, printer ink, black varnish, and as a filler for rubbers. Second is catalytic oxidation. When heated in a regulated supply of air or oxygen at high pressure and in the presence of suitable metallic catalyst, lower alkanes are oxidized to alcohols and aldehydes, while higher homologous yields long chain fatty acids. For example, when a mixture of methane and oxygen in suitable proportions is compressed to 100 atmospheres and passed through copper tubes at 475 Kelvin, methane is oxidized to methanol. CH4 plus O2 at 475 Kelvin and 100 atm pressure in copper tube converted to CH3OH. Normally, alkanes resist the action of oxidizing agents such as potassium permanganate, but alkanes contain tertiary hydrogen atoms can be oxidized by such reagent to corresponding alcohols. That is isobutane plus oxygen in presence of alcoholic KMnO4 converted to tertiary butyl alcohol. Thermal decomposition or pyrolysis is the fifth method. This process involves the decomposition of bigger molecules into a number of simple molecules by the action of heat. When heated to about 775 to 1075 Kelvin, higher alkanes undergo pyrolysis to yield smaller molecules. For example, propane decomposes as follows at about 735 Kelvin. Propane CH3 CH2 CH3 at 735 Kelvin converted to CH2 double bond CH2, that is ethylene plus methane, and converted to CH3 CH double bond CH2 plus H2, that is hydrogen is 45%, and in methane compound hydrogen is 55%. It is apparent that pyrolysis involves the decomposition of carbon-carbon as well as carbon-hydrogen bonds. The composition of products depends upon the nature of starting compounds and condition employed. The pyrolysis or thermal decomposition of alkanes obtained from petroleum is commonly referred to as cracking or fragmentation. Cracking is a very important process from commercial point of view and is discussed in detail under petroleum. Sixth method is catalytic reforming or aromatization. This process concerns the conversion of aliphatic hydrocarbons into aromatic hydrocarbons in the presence of suitable catalyst. The reaction involves dehydrogenation, cyclization, and even isomerization in some cases. It is generally carried out at a high temperature of about 720 to 820 Kelvin, high pressure, and in the presence of a catalyst, which generally consists of chromic oxide supported on aluminium oxide. Thus, N-hexane changes into benzene and N-heptane changes into toluene. N-hexane at 770 Kelvin and 10 to 20 atm pressure in presence of Cr2O3 and Al2O3 converted to benzene plus H2. These days the reaction is generally carried out at 670 Kelvin in the presence of platinum as a catalyst. Therefore the reaction is sometimes termed as platforming. Seventh process is isomerization. It is the process of converting one isomer into another. It is found that when N alkanes are heated in the presence of aluminum chloride and hydrogen chloride, they are converted into branched chain isomers. For example, N-hexane at 375 Kelvin in presence of AlCl3 and HCl converted to 2-methylpentane and 3-methylpentane. Thank you.